Welcome. My name is Wamozo Cosmas. I'm going to take you through a review of the iterative knowledge exchange between the deep learning and space-time spectral clustering for unsupervised segmentation in videos. We are going to go through the research gap, the introduction, the proposed method, and then the conclusion. As much as we know, it's hard for computers to discover objects, specifically moving objects in a video over space and time. It's a very challenging task. It's easy for us humans to look at a video and easily recognize that that's a car. We can even go further to recognize that it's model, but for computers, it's hard to do something similar when non-supervised. It's hard to perform unsupervised discovery of objects in motion over space and time. I'm first going to go through the key terms in the paper, then I'll go to the proposed solution. So one of the key terms is spectral clustering, which is one of the cores of the paper. For spectral clustering, the main aim is usually to construct a similarity graph between a similarity graph for all data points. You can choose to use a method like KNN, whereby if we have points A, B, and C, we shall come up with the Euclidean distances of these points, which means we have to generate Euclidean distances of 3 points, which means it will be 3 nearest neighbors. And that's just an example. You have to come up with a function for defining similarity between these points, and then you come up with a similarity graph. Like the example I've given, you can use KNN to come up with you use something like Euclidean distances to come up with the relationship, and then you generate a graph. After all this is done, you have to create a matrix, a matrix of these weights or these points. With this matrix, we can come up with the diagonal degree D, which we shall use to calculate the graph Laplacian. With the graph Laplacian, we can use it to come up with the Euclidean vector, the eigenvectors and eigenvalues, with the goal of coming up with the minimal graph cut. With the minimal graph cut, I mean if you have like points like 4, 3, 2, 1, then -2, -3, -4. The minimal graph cut is usually the first non-zero, the least non-zero point, in this case, which is 1, before we hit the negatives. So usually we use that as the cut, so that points that are above that cut can be clustered differently and in a separate cluster, and then the points below that can be clustered in a separate cluster. As you can see, initially you have like your data points, then you can use a classical clustering algorithm like k-mean to partition the embedding space. And then after partitioning this embedding space, you can go ahead and get the Laplacian value, the Laplacian matrix, and you come up with the Euclidean, the eigenvectors and eigenvalues, which you can use to generate the minimal graph cut and come up with your clusters. So that's generally spectral clustering. And the next term is deep neural network. And these deep neural networks are just neural networks with at least 2 layers, at least 2 hidden, just like you can see they have at least 2 hidden layers. You have the input layer and then the output layer, but in between you have more than at least a minimum of at least 2 hidden layers. That becomes a deep neural network, which can be referred to as a deep net. Then video object segmentation. In computer vision, there are like 3 phases you go through. One is classification, object detection, and then object segmentation. With classification, obviously, you have to first identify what something is, and then you're able to classify it as maybe this is like a pig. And then with object detection, we have to draw a bounding box around that object. But that box doesn't always bring out the actual shape of measurement properties of that particular object. That's why we have to go a step further and introduce a concept of object segmentation. In object segmentation, we have one of the reasons why we need segmentation is, like I say, the bounding box is usually rectangular. So if you look at this peak has a curvature. So you can't come up with the shape of the pig if it's in a bounding box which is rectangular, because it will be hard to know the area of this pig and the perimeter of this pig, because the box doesn't bring it out properly, because this pig has a curvature. So that's why we have to come up with the concept of object segmentation, which is just an extension of object detection, where we mark the presence of an object through a pixel-wise masks, the pixel-wise masks that are generated for each object in an image. Yeah. So this is more granular than just using a bounding box, since it can help us determine the shape of each object present in the image. Since we are familiar with the key terms of the paper, we can now dive deep into the proposed solution. The proposed solution for the other research gap of coming up with unsupervised object discovery, specifically for objects that are in motion in a specific space and time. The authors suggested a dual system for unsupervised object segmentation, in which we bring together 2 modules that complement each other, where we have our spectral graph neural network, which is responsible for coming up with the classifications which are passed on to the deep net. Like I say, the deep net requires some supervised data, which usually comes from the spectral graph. And then also the spectral graph might require new nodes to continue to make better classifications. So the output of the deep net is given back to the graph node in an iterative process, whereby they keep on exchanging data. In that process, each one of them keeps on canceling out the other's weakness. In a way that deep nets require supervision, which that supervision will come from the spectral space-time graph, and spectral space-time graphs require deep node levels, and so they require additional nodes to enhance their classification. So which will come from the output of the deep net. The deep nets, since the deep nets are good at extracting features from data, so both these algorithms complement each other in a knowledge exchange paradigm, whereby they keep on exchanging knowledge to each other until they reach consensual convergence, whereby they will both agree that this is the maximum they can do in terms of classifying and extracting features in the video shots. This is the flow chart. This is the flowchart of the algorithm. As you can see, here we pass images, which are like video shots, to the graph module. And when we pass these images, the algorithm generates a future motion adjacence matrix, which it passes to the graph, so that the graph is able to classify these video shots and generate an output, which it passes to the deep net. The deep net is able to extract features, and it's able to pass these features back to the graph module to continue classifying them until this process is done, until they reach consensual convergency on the output. So yeah, that's the entire algorithm. For the conclusions, the iterative knowledge exchange system that proposes an exchange paradigm between spectral space-time clustering and deep net is a very, very good algorithm which cancels out the weaknesses of both algorithms and maximizes the strength of both algorithms. But it seems there was little attention given to the computational complexity of the algorithm, because both of these are very complex algorithms which require heavy computational resources for each iterations, whereby the final computation of the computational overhead of this might be a big O of n3, whereby throughout each iteration, with more data provided to each algorithm in the exchange, might result in heavy computational needs. It might result in additional complexity, and hence the algorithm might be computationally expensive to run with additional iterations made. So there was less attention given to the computational complexity of the algorithm, but it's a good proposal, and it can help in the object discovery in unsupervised environment. Yeah, thank you. That's all I had for you.